Hello everybody, welcome back. In my previous videos, I received a few requests about 3D player movement. On the internet there are already many great tutorials that explain how to do that, but many just focus on the movement in 3D space without integrating animations and may feel too basic, while some other use finite state machines to deal with animation that may be too difficult for others. So I decided to make a personal version of Simple Player to fill that gap. We start by creating a new 3D scene. We add a kinematic body as a root node. Then we add our character model. Please pay attention and rotate it so that the axis, the blue one, points behind the character. Then we add a collision shape, and we pick a capsule shape that we adjust in size and position to contain our character. Last, we add our camera setup. It is composed by a position 3D that we call simple camera, another position as a child that we call pitch, then a spring arm, and finally a camera. Later, we will add a script to control the camera and the simple camera position node. Leave the position node in the same origin of the character and adjust the camera position by moving and rotating only the spring arm and the camera itself. When you are satisfied, we can save the scene and add a script to Simple Player root node. To test following scripts, I made a small test level. There's a stair and a small slope to test jumps and sliding. Simple Player script has already all versions of 3D movement. You will find all steps commented in the repository linked in the description. We start by looking at all variables. We have references to base character and a simple camera. Then we have a few export vars for speed, used for movement, gravity, and then the number of air jumps and left jumps that we will use later to implement double or multiple jumps, a jump impulse, and then a vector 3D to keep track of character velocity and another vector 3D named target. We will see this in a moment. Ready function is empty. All the code for movement is in physics process. For the basic movement, we take inspiration from the classic bin or peel tutorials. First, we set up a snap vector that is useful to prevent sliding on slopes. Then we get input direction. As you can see, with this single line of code, we can get a vector 2D that maps the movement from our inputs. If we check the input map, you can see that movement maps both keyboard WASD keys and controller left analog stick. This one line does all for us. Then we map the input to movement, as we have to remap y-axis from 2D to z-axis in 3D. If the movement is greater than a given threshold, we update the target position, interpolating its current value with the moving direction. We use this vector to direct the character smoothly, using lookat function. Pay attention, we need to set the target y value to avoid unwanted tilting of the character when jumping or going down gaps and slopes. After changing direction, we apply gravity using a separate variable called fall velocity, and we apply it to the actual velocity only after the update of movement on x and z axis. Finally, we apply the movement using move and slide with snap. This function applies movement as a regular move and slide, but prevents our character from sliding down slopes when we are not moving. We save and play. As you can see, if we climb the small slope, we have no problem and the character stays in place. In the file, we also have a regular move and slide, and we can swap comments and try it. The character slides down the slope. This can still be useful for a wheeled character or if your character is trapped in a ball. You may have noticed that my movement was quite strange. That's because it was based on global coordinates. So the next step is including camera. We add a script to simple camera position 3D node. In process function, we check input. We can see we mapped arrow keys and right controller stick. Then we apply rotation to two different position 3D nodes, simple camera itself and pitch. Using two position 3D nodes is useful and makes rotation simple. We could expand camera management in future. For this tutorial, this is enough. In player script, we just need to change a single line. We have to remap input direction multiplying it by camera global coordinates. Next, we add jumps. After fall velocity, we add a check to verify if player is on the floor. If so, we edit fall velocity by applying a positive impulse, gravity as a negative value. But if we are using move and slide with snap, remember to set snap vector to 0 to allow player to detach from floor. This value will be reset anyway on the next execution of physics process. We can test this and it works. We can still expand this by adding double or even multiple jump logic. We use an export var to set the maximum number of air jumps and a counter to keep track of left air jumps. We first add an else statement. If the character is on ground but not jumping, the number of left air jump is reset. Then we add another else statement that will be enabled when the player is in air, jumping or falling. In this case, we add another if that captures jump inputs. If jump button is pressed and the counter is still greater than 0, we apply another jump impulse and decrease the counter. We don't need to act on snap vector as the character is already detached from floor. Now we can test it. As you can see, we can use a very high air jump number to implement a Kirby-like floating, and we could also remove the counter completely if we want to implement a flying logic or maybe even a swimming logic. And finally, we add animations. We won't implement a finite state machine, but we will actually use one already provided in Godot. By checking the code, you can see that at the beginning of the physics process, we added a new var called nextAction that we assign with value idle that we access through our base character class. In case of direction change, we assign move action. And we do the same in case of jump air action. At the end of the function, we call a method on base character called doAction, where we pass current action and character velocity. Now let's go and check base character. As you can see, beside the variable used to update the looks, we have an enum with currently supported actions, and a var to keep track of current action that we set idle as default. To understand this action, let's go to 3D view and then we add an animation tree. In inspector, we set tree root as animation node state machine. Then we assign our animation player and set tree as active. We will use the finite state machine provided by this node instead of writing one from scratch. This may not be the optimal solution, but it is possible to reduce a lot of code while taking advantage of a built-in node. In animation tree panel, we right-click and add idle animation. We name it idle. Be careful, we need to use the same text used in the enum. We set idle as a start animation using the A tag. Then we add a movement state called move, but instead of using a simple animation, we use a blend space 1D. This will support a smooth transition between walk and run animation, and it is ideal for analog controls. By the way, it is crucial to use also all capital letters for the name, exactly the same as in the enum. We connect animation using the arrow tool on top left of the panel. Clicking on the pencil, we can edit the blend space. We remap the range of the blend space to go from 0 to 1. Then we add animations by right-clicking. We have walk and run. And we use the cursor tool to place them in the best spot for blending transition. Remember to test animation to check if loop was activated, and if necessary, you can always fix them in animation node. And then we can activate the tree and select the move node. Open editing and we can drag around the blend value to check the transition. By clicking on each connection arrow, we can edit the crossfade time in the inspector. This will blend different animations during transition. Usually I pick a low value between 0.3 and 0.5, but you should test to find the best solution for your animations. Lastly, we add jump animation and call it air. We connect this to the other animations. At the end, we remove one of the connection as after jump we need to fall back to default idle state. Let's go back to the script. We have a reference to animation 3 and parameters playback that we will use to trigger state change from code. Let's check the action function. The action parameter is an integer. Enums are not supported as type, but we can use them in type GDScript using int values, while direction is a vector 3. The first step is updating the move direction. We subdivide it by 10 to map the value between 0 and 1, and then we round it and assign it to the blend parameter for move. Be careful when you write this string. Actually, we would need to update this value only if move action is in execution, but considering that we call do action basically every frame anyway and it does not interfere with other state, this is a good place. Also because the next step is checking current action and return if we provide the same action. This pattern is very useful to avoid restarting animation over and over every time. If it is a new action, we update current action. Then we retrieve the action name from the enum using the int value as index. Then we pass this string to the travel function that reaches the desired animation following a path in our animation tree. You can notice that everything works fine, but there are actually two small problems. One, the jump has a full animation that does not get along very well with our jump impulse and timing. So I create a new simpler animation that will be snappier, actually reducing the number of frames. The second problem is that when transitioning between walk and run, we can see that the character is shaking. This is due to analog stick mapping. Even if we round the value, if it is very sensible, it may be shaky. I ended up replacing the mapping with a buffered mapping. Let's uncomment the function and see how it works. We use three variables stored globally in the script. One is to keep reference to candidate velocity. Then we have a size for the buffer and a counter. We pass the velocity length to buffer velocity function. We divide it by 10 and round it as before. Then we compare the value with current velocity candidate. If it is different, it becomes the new candidate and we set the counter to 1. Otherwise, we increase the count and, if we reach the buffer size, we pass the value to blend parameter. We can test it and see that it works. It looks like a small buffer or 3 value is enough. Anyway, you can test bigger buffers. That should not affect the responsiveness of character. That's because the movement is executed anyway and only the animation blend is affected by the buffer. So that's all for now. I hope you liked it, and if you have any comments and requests, please leave a comment below. Thank you very much. See you next time.